Hi, today we are going to talk about geometric extremas in the complex plan, and this is our team members. I'm Chong, the technical editor and coordinator. Our intro and objective include core goals, which is analyze the boundary of complex loci, dual methodology, which is rigorous manual algebra, and visual justification. Validation part to ensure both methods match, and the representation of complex number.
Hi, my name is Lim Jia Yi, and for our circular locus, we chose a radius of 4 and a center point at 3 plus 4i. Before that, we converted this into a Cartesian equation by substituting z0 and z. After squaring it, we get this equation. To find z-min and z-max, we use the Pythagoras theorem to get the distance from the origin to our center. And for z-min, we calculated using this, while for z-max, we used this. Next, we need to define the line passing through the origin and the center. Using this formula, we find an m of 4/3 to get y equals to 4/3 x plus 0 as the line intersects at the origin. Now, we need to calculate the intersection coordinates. By substituting linear function that passes the origin and locus into our Cartesian equation and factorizing it, we get x-intercepts. Using these values, we find the 4 y-intercepts. For our final complex numbers, we get these. Lastly, we need to prove this. By dividing z0 by its modulus, it creates a unit vector pointing straight to the center of the circle. Multiplying radius scales this vector to reach the circle's edge. Adding or subtracting this scaled vector from our center point calculates the exact extreme points. Substituting our numbers into these formulas, z-min and z-max are evaluated as such. This matches our simultaneous equations perfectly, confirming our results.
Hi, my name is Syiffa. I'm as Algebraic lead circle for this project. So first thing first, if we want to find the minimum and maximum argument, we must know where is it actually. So this is my perspective, and the lower will be the minimum, and the upper one will be the maximum. So to find this tangent, we must use y equal to mx. The reason why we use y equal to mx is because this tangent is across at the origin. So because of that, c equal to 0, so we use y equal to mx. So we must substitute y equal to mx into the Cartesian equation. So after we derive it like this, so we can know the value of m. So after we know it, we must substitute in the equation is on here to find the Cartesian equation of z minimum at maximum. If we want to know the degree, it's going to be like this. Since z maximum at the quadrant 2, we must minus it with 180 degrees. So this will be the degree of this z argument.
Hi, I'm Ainul, the GeoGebra architect for this group. I'll be doing the visual justifications for both methods. So, for the circular locus, I use the sweeping circle method. As you can see, it first touches the boundary at r equals to 1 for magnitude of z minimum and perfectly inscribes it at r equals to 9 for magnitude of z maximum. I then plotted the tangent rays by substituting the m values obtained into this equation. You can see that these rays intersect with the locus at exactly our calculated coordinates, confirming our argument extremas. Now, moving on to our next point.
Hi, my name is Hazel. Now we get into the algebraic calculation of ellipse. So first we have to determine the value of z1, z2, and a, which is 1, 0, 2, 0, and 5. So firstly, we have to convert the equation into Cartesian form, which we will get this. Next, we have to use the isolate and square method to get this equation. And now, we have to use the isolate and square method again to get this equation. So for the final step, we have to use computing the square method to get our final answer. Now, we want to calculate all the argument extrema. So firstly, we have to substitute y equal to mx equation into our previous ellipse equation. Hence, we will get this equation.
Oh, why should we set discriminant to 0?
Why do we have to set discriminant to 0? Because for extreme arguments, the line from origin must touch the ellipse, meaning it is tangent. Hence, this is why we must set the discriminant to 0. So, we set our discriminants to 0, which is b squared minus 4ac equals to 0. Now we substitute our values from the previous equation to get the final value of m, which is positive and negative. So now that we found our values of m, we substitute into our equation of m equals to tangent theta to get our value of maximum and minimum argument.
To find the z-max and z-min of the ellipse, first we need to define the distance formula. By substituting y from the derived ellipse function into the distance formula, we get this. And then, after finding the derivative and setting it to 0, we find x. Now, we need to check if our x is inside the ellipse's domain. Calling the ellipse equation, we can find that the horizontal radius, and after finding the upper boundary and lower boundary, we can determine that our x is sadly not within the boundary. And following this, we can see that over here, z-max is this, while z-minimum is this, as our coordinates lie on the x-axis.
Hi, so we meet again. Just like the circular locus, the sweeping circle identifies the point of intersection at the nearest and furthest curves of the ellipse from the origins, which are these. Finally, I applied the same tangent rays method to the elliptical locus. The intersection points match our algebraic calculations for the argument extremas perfectly, providing the visual proof for our final results.
Next, visual versus algebraic verification. For the circular locus, we obtain the Cartesian form. GeoGebra confirmed this with a center at 3, 4 and a radius of 4. The modulus extrema match the intersection points. For the elliptical locus, expanding the distance sum gives the standard ellipse. The semi-major axis is 2.5 and the semi-minor axis is 1.5, matching the algebraic denominators and confirming the foci. In conclusion, the match between algebra and GeoGebra validates our results. Both methods give the same answer. Thank you.